Hello. This lecture will cover pages 62 through 63 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 4A, Closed Loop Feedback Analysis. We're going to start on page 62. And before we start Chapter 4, what I want to do is I want to talk about closed loop feedback analysis a little bit. You're going to see this in other courses, and I want to introduce it to you in this course, and this is a perfect chapter to do that. What we're looking at here is a basic block diagram of a closed loop control system. We have an input voltage coming in over here that comes from many different inputs, and I have a list of some inputs here. Temperature sensor, maybe a pressure sensor, maybe a level sensor in a tank, maybe a speed sensor on a motor or a conveyor belt, or a gyro to determine whether there is an angular displacement per second. That's what a gyro will do, a gyro sensor. They're all coming from sensors, and they're represented in a lot of cases as voltages, sometimes as currents. You'll go through a control system here and you'll produce an output V out. That output goes to control maybe a heater, maybe a pump or a valve, maybe a motor, or maybe the thrusters of a jet rocket. So on your inputs you'd have temperature to control a heater, as an example. You'd have pressure to control a pump or a valve, or level in a tank as an input, and you'd control a pump or a valve. The speed is an input to control a motor or a conveyor belt. The gyro as an input to control the thrusters of a jet or the thrusters of a rocket. This control system right here attempts to stabilize the outputs, and it does it by manipulating what it sees on the input. And this is an example of a block diagram that attempts to simplify, and you can take a lot of electromechanical systems, pure electrical systems, some electromechanical, some purely mechanical systems, and you can boil them down to a simple block diagram. This has feedback in it. It takes an output and it feeds it back around to the input. Sometimes it takes the entire output, where this is just a line that comes back. And this H parameter, which we'll talk about in a minute, is a 1. It basically takes the full output and brings it around. Sometimes it takes a portion of the output. Sometimes it takes a multiplication of the output and it brings it back. And it could bring it back as negative feedback, or it can bring it back as positive feedback. We're not going to use positive feedback. Very rarely. Positive feedback has applications, but very rarely are you going to bring the output signal back and feed it with positive feedback. It leads to oscillations. This chapter, and in future courses, 98% of the time you're taking the output and you're bringing it back with negative feedback at this summing junction. So let's take a look at some terminology here. This G they refer to as a forward transmittance function, and this H they refer to as a feedback transmittance function. Forget about the terminology for now. This G is just a simple multiplier from this point to this point. If you have 1 volt coming in and this is a gain 10, you get 10 volts out. So G is just a multiplier in this direction. It's a gain. This H is a gain also, except it's a feedback gain. Look at that direction of the arrow. If you have 10 volts out here and the H is a 0.5, you get 10 times 0.5 or 5 volts back here. If H is a 1 when you have 10 volts out here, you're feeding back 10 volts. So H is just a multiplier as well. What we're going to do is we're going to analyze this, and we're going to look for the closed loop gain of this system, whatever it may represent. It could represent many things. Our definition of closed loop gain is just like our definition of open loop gain was. It's V out divided by V in, or in this case Vs. Now, from this point forward, you have to recognize the fact that we're going to have voltage gain closed loop, and we're going to have voltage gain open loop. And the open loop voltage gain is not the same thing as a closed loop voltage gain. They're two different gains. Open loop voltage gain looks like this, where you have V in here, or Vs, and you have V out at that point. If this gain here, if this open loop voltage gain that I'm showing you here is 10, and you have 2 volts in, you get 20 volts out. It's just a multiplication factor. The voltage gain is defined by V out over V in, but that's open loop because there's nothing being fed back to this point when I show it like that. And that's simply equal to V out over V in. And in this simple example right here, that was 20 over 2, and you're right back to the voltage closed loop, the open loop voltage gain of 10, which is what I've shown you here. Anytime you bring a portion of this back, or you bring some of the output back like this, through some other parameter here, which we called H, that's going to be referred to as the closed loop voltage gain because you're closing the loop. So if you take a look at this, this is a closed loop voltage gain when we form the ratio. And what we need to do is work toward getting the ratio of V out over Vs. The way we do that is we define something called an air signal right here. This is an air signal E. And the purpose of that air signal is to take what's coming from the sensor and a little bit of what the output's trying to do to control the device and make correction. So it keeps this stable or keeps this controlled. So let's define the output in terms of the air signal. Can everybody look at this equation and see that the output V out is simply equal to E times G? Forget about this down here. We don't have to worry about it. Look at this open loop. Break the loop here and just look at this open loop G here. E times G, open loop, gives us V out. And there's the simple equation. Well, let's take a look at what E's made up of. E's made up of a summing junction here of Vs and minus, we're going to use negative feedback, so we're going to use a minus whatever's down here. Well, what's down here? It's V out times H. Here's V out, and you multiply it times H to give you that here. So V out times H is what's here. So what is E? E is simply equal to the plus of Vs, that's a summing junction, minus V out times H. We're assuming negative feedback. Now I think you could look at this equation for E and you could substitute it in here and you can get what V out is. V out is simply equal to E, which is the substitution of this into there, times G. So we move from this point down to this equation. Now, all we need to do is form the ratio here of V out over Vs, because that's the definition of closed loop gain. So we isolate V out, a little bit of algebra here. You can follow through here and see this. It's pretty easy to understand. And you form the ratio V out over Vs, and you end up with G over 1 plus GH. In other words, the electrical engineer knows on this block diagram, because it's very, very popular, and like I said, you're going to see it a little bit in this course, but you're going to see it a lot in future control classes. It's G, this open loop gain, G, divided by 1 plus the open loop gain times this feedback factor H. What engineers do is they look at this and they say, what is this equation really telling you? It's telling you that when you get it boiled down to this block diagram, the closed loop gain, this divided by this, is equal to the forward gain. They call that the forward gain. Divided by 1 plus the loop gain. The loop gain is this. You start here and just go around the loop. G times H. So the closed loop gain is equal to the forward gain, G, divided by 1 plus the loop gain. Now, if it's negative feedback, you get a plus sign there. If it's positive feedback, you get a negative sign there. That's how the algebra works out. Very important equation. So I'm going to take that equation and look at the next page, which leads to the most important equation in control system theory. The closed loop gain, V out over Vs, is equal to G, which was the forward gain, divided by 1 plus, because it's negative feedback, the forward gain times the reverse gain, which is the feedback gain, which is simply the loop gain. We're going to refer to that as equation A. If there is an input function C, an input network C, the block diagram would look like this. In other words, if you have some gain factor, another preamplifier or something that's driving this because you need to get this signal up a little bit, that C just goes in as a multiplier. Here's C, just goes in as a multiplier, and then your gain there is your G over 1 plus GH. We're going to refer to that as equation B. Keeping in mind that both of these equations here you're going to see coming up here in the next lecture a little bit. We'll refer to them a little bit, but you're going to see them a lot in future classes. Now, some students say, well, how do you get a negative gain, or how do you get a positive gain? I'll show you where we're going with this. We're going to have in the next lecture operational amplifiers, and an operational amplifier is going to look like that without that being V out, and it's going to have a non-inverting input, which is the plus input, and it's going to have a inverting input, which is a negative input. It's a 2-input device. That's an operational amplifier. If you take the output or a portion of the output and you feed it back, and usually we're going to feed it back through a resistor to the input, and that input is the inverting input or the negative input. That's called negative feedback. That's how you're getting negative feedback. Now, I don't care if you do it this way or you draw your operational amplifier, and sometimes they put the negative up, they put the inverting terminal up here and the non-inverting terminal down here. Here's your output here. If you take a portion of that output to a resistor, in most cases, not always, and you take it around to the inverting input or the negative input, that's negative feedback. These are the same circuits. They're exactly the same circuits. You just have these inverse inputs switched. Notice the output goes back to the inverting input, the negative input. Positive feedback we're not going to be using, but it would just simply look like this. You have a plus, you have a minus, here's your output V out. You take the output and you feed it around to your positive input, to your non-inverting input. That's positive feedback. That's how you end up with positive feedback. We're not going to worry about this. You won't see any circuits like that in this course. They'll all look like this with resistors in them. So as a quick review, I showed you how to take a block diagram of a closed loop feedback system, boil it down to this. You have inputs and you have outputs, and the purpose is to control that output based on what you're seeing on the input. And what are some of the inputs and what are the outputs they control? These are voltages in both cases. These inputs, again, can be temperature, controlling a heater on the output with a voltage, or pressure, coming from a pressure sensor. These are sensors. Controlling a pump or a valve, or a level sensor, controlling the level in a tank, either a pump or, through a pump or a valve, or the speed as an input, controlling a motor, or a gyro, controlling the thrusters of a rocket. And to give you an idea here, just picture this one as a final closing on this lecture. You're trying to control the thrusters of a rocket here, and you have a gyro. And that rocket is blasting off. And picture 4 thrusters at 90 degrees apart from one another in the base of that rocket. If that rocket starts to blast off and all 4 thrusters are equal, it should go straight. But let's say for one reason you get a wind start to blow. or one of the thrusters, the thruster on the right, picture this, the thruster on the right starts to lose power. As it's gone vertical, if the thruster on the right starts to lose power, that rocket's going to tilt to the right as it goes higher and higher. So you would have a gyro sensing that, and you could go ahead and control the thrusters, that particular thruster. Give it more voltage. Give it more power. So that's how this control system works, controlling those outputs with these inputs. And that concludes this lecture.